Iris, welcome, and the floor is yours. Oh, I think you are muted, Iris.
Is my slides now visible?
Yes.
Okay. Well, welcome everybody. And today I will give a presentation on the KNMI climate scenarios for the Dutch Caribbean. So today we'll talk about the Caribbean region. My name is Iris Keizer and I work at KNMI as a climate scientist. I studied physics and then I specialized in the climate and first focused on sea level rise, but now I focus on the Caribbean climate scenarios. So we made these climate scenarios for the BES islands, that's Bonaire, Sint Eustatius and Saba. And therefore we looked at these 5 variables. So we looked at temperature, rainfall, wind speed, sea level rise and hurricanes. And that's what I will talk about today. So as I already mentioned, I work at the KNMI, it's the Royal Netherlands Meteorological Institute. Here you see our office, that's where I am now. And the Dutch Caribbean islands, Bonaire, Staysia and Saba, that you can also see on the slide, are part of the Netherlands. So they're special municipalities of the Netherlands. And that's why as an institute, we also focus our climate research on these areas. And not only the climate research, we also do our seismology research there. And we also do the weather forecasts for this area. So this is the team that worked on the Caribbean climate. So these are my colleagues. Peter Sigmund is our project leader. Nadia and Hilke, who are maybe also now watching along, are the people who looked at the hurricanes for the Caribbean region. Rein, I also saw he's with us today. He's started doing the research for the Caribbean together with Marta. Marta was a study friend of me that after her studies worked on the Caribbean climate scenarios, and Marta really did all the work to provide the scenarios on temperature, rain and wind. And since May, I took over from Marta and will continue this effort. And Davy is our sea level expert. So he does sea level research for both the European Netherlands and also for the Caribbean Netherlands and made the sea level scenarios. So next, I'll first talk a bit about the observations. This is work we already published before in the KNMI Klimaatsignaal 2021. And there we looked, for example, at the observations of temperature and precipitation. But it's one of the biggest problems with looking at climate information for this region is the availability of good data whereof the time series really span a long period back in time. So for example, for temperature, we didn't have those for the islands we were looking at. So we took the temperature time series from other islands as proxy data. So you can see that the upper plot is the temperature from 1960 till about now. And we took the data from Curaçao and Sint Maarten. And Curaçao is at about 50 kilometers from Bonaire, and Sint Maarten is also at about 50 kilometers from the other islands. So it's a well enough proxy. And what we see is that there's a small trend in the temperature. So there's a trend of 1.5 degrees Celsius per century. And what we see in the precipitation data, that's the lower plot. There we took actually data from the islands themselves. And there's a problem that there's a really large interannual variability. So this means that from year to year, the amount of precipitation or rainfall, it can vary by a lot. And that's what makes it really difficult to estimate a trend. So in the observations of precipitation, we don't see a trend. So for sea level rise, we looked at satellite data, and satellite data for sea level rise is available from about 1993. So here we looked at the sea level rise from 1993 to 2019, and we really see a trend in sea level rise in this region of about 31 centimeters per century. And you can also see that there's quite some regional variability in the sea level rise. And we compared this data to data from Puerto Rico to see if the satellite data compares well to a local observation station. And this means that since 1993, the sea level rise was about 10 centimeters. So we also look at hurricanes. They, of course, have a really large impact in the region. And this impact is, of course, largest near the center of the hurricane. So it can be, you can feel the impact up to 500 kilometers. But we looked at storms that had a maximum wind speed of 18 kilometers per hour, and that were within 250 kilometers of an island. So here you can see the storm tracks that were near Aruba, Curaçao, and Bonaire. And here you can see the storm tracks and hurricane tracks that were near Saba and Sint Eustatius. And you can already see in the plot on the right that there were a lot more storms and hurricanes near these more northern islands. And that's also where, most storms and hurricanes come by. So we calculated the return periods for these islands. And this is for Saba and Sint Eustatius, so the northern islands, where you can see that a storm or hurricane of category 1 has a return period of about 2 years, and of category 5 of about 40 years. So that were the observations, and in our most recent results, we published the KNMI 23 climate scenarios. And well, the effort we did there was translating the scenarios that are presented by the IPCC reports. Here you can see the IPCC report. They have different working groups, and the working group we are mostly interested in is the working group 1, which is called the physical science basis. And there they look at climate change at a global scale. And we translated this data to the local scale for both the European Netherlands, but also for these 3 Caribbean islands. And that's what we call the climate scenarios. So the climate scenarios are future projections, and there we adopt a storyline approach. So what's the climate scenarios? It's a plausible and coherent description of a potential future climate. And we calculate multiple scenarios, and we do this to span a range of potential future climates. And that's needed because there's different uncertainties. So there's basically 3 sources of uncertainties that we take into account. Of course, we cannot look into the future. We do not know what decisions will be made, how people will act. So there's this uncertainty about future emissions that we take into account. And there's the uncertainty about the climate response, what we also call the climate sensitivity. So that for a certain amount of emissions, there's an uncertainty in how climate change will be. And that's different in different climate models that we use. And then the third uncertainty is that there's an uncertainty due to internal variability of the climate system. As I already showed the observations of the rainfall, of the precipitation, you see a really large year-to-year variation, and that's variability. And that we have this internal variability on different timescales. So this is a year-to-year variability, but you also have variability for different decades or longer time periods. So yeah, this is a plot of the global emissions of CO2 over the past, where you can see that it's still continuing to increase unless, even though there was a little drop due to the COVID-19 pandemic. And based on this amount of emissions of CO2, the IPCC makes different scenarios of what they think the CO2 emissions will look like for the future. And from these CO2 emissions, they then also have different scenarios for temperature. So these CO2 emissions, of course, drive global warming, and these figures show that we already can really see global warming. So on a global scale right now, we are already at a global warming of 1.2 degrees Celsius, so compared to pre-industrial. And that's what's shown in these climate stripes here at the bottom of the slide. These climate stripes are really well known and shown a lot to show that global warming is happening. And what they are showing is the temperature change over a long period, and then every bar is 1 year. And since the blue bars are the colder years, you can really see, and the red bars are the warmer years, you can really see that global warming is taking place. This is also shown in the plot on the left, where you see also the colder years are the years more from the past, and you can really see that the years more to the future are getting warmer and warmer and warmer. But what this plot also nicely shows is that 2023, so this year is quite an outstanding warm year. It's on track to become the warmest year since we measure this. And you can also see that there's this light gray line, that's the 1.5 degrees above the pre-industrial level. And that's what in the Paris Agreement we agreed upon, like we will keep global warming limited at 1.5 degrees. And you can see that this year in 2023, it was already for multiple periods of time above this level. And here on the right, you can see the temperature anomalies for September on a global scale. And also you can see that especially the month of September this year was a really large anomaly on a global scale, but also in the Caribbean. So especially on, for example, Curaçao and Bonaire, schools had to close and workers had different time schedules because of the heat in September. So partly this heat in September was due to really warm sea temperatures in the North Atlantic. So here you can see the North Atlantic. It's now still anomalously warm, but it has been anomalously warm for a couple of months already. And as a lot of you may know, is that we are now also in an El Nino cycle. And that means that this is the Pacific Ocean, that around the equator, the east part of the Pacific Ocean gets anomalously warm. And you can really see these dark red colors here that show that there's a really strong El Nino happening right now. And this is also driving up these global air temperatures. And this recently resulted in another record. And this has happened for the first time in records. So on the 17th and 18th of November, we first crossed the +2 degrees compared to pre-industrial for a daily record. So this is the global warming we've already observed and that we're seeing now. And that's shown here in the blue plot. And from this global warming, the IPCC makes these different scenarios for the future. And this blue scenario is the scenario that's in agreement with the Paris Agreement. And that's you can see that in 2100, we stay well below the 2 degrees warming at 1.7 degrees of warming. And the orange scenario is the scenario that's what's business as usual. So that's what we're on track for, which ends up where we end up at 2.7 degrees of global warming. And there's this really high-end scenario that goes up to almost 5 degrees of global warming. And as I said before, so there's an uncertainty in the amount of emissions in the future, and these scenarios show this uncertainty in emissions. And thereof we pick two scenarios. But the spread around this median, that's the different climate models give us different results given this emission scenario. And that's what we call the climate sensitivity. So that's the second uncertainty that's also included in our scenarios in this bandwidth within a scenario. So we picked these two emission scenarios, the high CO2 emission scenario and the low CO2 emission scenario, and thereby we span this uncertainty in the future. And then we make scenarios for the low emission scenario and the high emission scenario for two target years. So we look at 2050 and we look at 2100. So we also look at the uncertainty in precipitation, which is very important for the Caribbean region. So what you see on the plots here is what climate models project is the change of precipitation in 2100. And this is for the high emission scenarios. And what you can really see is that there's a dry group of models that is shown on the left for both the dry season and the wet season that show that there's a really strong decline in precipitation in 2100. And some models even show a decline of up to 50 or 60%. And on the right, you see that there's also a group of models that hardly show any change in precipitation. So there's no trend. And we also make scenarios for these two groups of models, so that give us a drying climate and a wetting climate, where wetting climate doesn't mean it gets wetter, but it's the wet variant. So we also make scenarios for the dry and wet climate, and that we do that for the atmospheric variables. So only for temperature, rainfall, and wind speed, as this doesn't matter for the sea level rise, for example. So that gives us four scenarios. So I explained already that we look at the high emissions and low emissions, and that we look at the dry group of models and the wet group of models, and combining those gives us four scenarios. And then we look at changes for both the annual mean, but also in the Caribbean region, we have two seasons. We have the dry season and the wet season. So we also look at changes for the dry and wet season. And then we calculate these changes for the variables. And that gives us a huge table with a lot of figures, a lot of numbers. And I'll go a bit through them. So as it's explained, we have the change for the year, we have the change for the wet season, the change for the dry season, we have our sea level variable, we have temperature, precipitation, and wind. And then we look at our two target years. So we look at 2050 and 2100, and then we have our four scenarios. So that's a lot of numbers that we obtain. And I will now go in a few slides through in more detail to a few of the changes. So if we look at temperature and precipitation, these are the time series that result from our calculations for, on the left, Bonaire, on the right, Sint Eustatius and Saba. And the upper plot shows temperature and the lower plot shows precipitation or rainfall. And you can see that there's a really big difference in 2100 between the low emission scenario and the high emission scenario for temperature, but also for the median in precipitation, for example. And what we see is that for both seasons and all islands, it both gets warmer and drier. And for the precipitation, we see a really large intermodal spread. Yes, then the sea level rise. So this is the plot of the sea level rise until 2100. And here we also look at the low emission scenario and the high emission scenario. And we see that for low emissions in 2100, sea level rises between 30 and 80 centimeters. And for high emissions between about 55 centimeters and 1 meter 30. Here I show the sea level rise figure only for Bonaire, as there the impacts are biggest, because this is really a low-lying island where the other two are volcanic islands. So there's not a lot of area below 20 meters. And we also make for sea level rise 3 special scenarios, because the sea level rise can be a lot faster if some processes occur before 2100, like the Antarctic ice sheet can become unstable. And this instability or this collapse of ice sheets is not well represented in the normal climate models that we use. So we try to include those scenarios that don't have a high chance. So they have a low probability, but the impact will be strong. So we also show them so that people know this might also happen, but they're not the scenarios to look at for decision making. And we see that if we include those scenarios, the upper limit of sea level rise can already reach 3.4 meters in 2100. And sea level rise is one of the variables that really will continue to rise for hundreds or thousands years, even if we keep emissions low. And that's because the ice sheets respond very slowly to climate change. So the ice sheets have not yet adapted to current warming, so they will continue to adapt, and then sea level will continue to rise. And we see that in this scenario that we really recently published, where we look beyond 2100 to 2300. And there you can really see that even for the low emission scenario, sea level rise will already be between 0.7 and 1.9 meters. And for the high emission scenario, it will already reach 7 meters. And then again, if we include these low likelihood, high impact scenarios, then the upper limit can reach even 20 meters. So that's a lot of sea level rise. So as I already mentioned before, we also look at hurricanes. But for the hurricanes, we cannot use the same method as we used for the other variables. But because hurricanes have really high impact, so they have, of course, the high wind speeds, the storm surges, and the rainfall. And they occur, as I already showed, more often in the Caribbean. It's really important to also look at them. And therefore, we use 2 different methods. So the first method is done by my colleague Nadia Bloemendaal. She made this model STORM, and that's a statistical model where she's able to make a synthetic data set to calculate return periods. Because the problem is that if a hurricane happens only once in 100 years, for example, and you only have data for the past 50 years, it's impossible to calculate the return period of this hurricane. So during her PhD, she made this data set where we have, this is the storm tracks for 1,000 years of data, but she created it for 10,000 years of data. And from that data, you can then actually calculate the return periods for hurricanes and also how they change in a changing climate. And there's been another experiment, a future weather experiment, we call it. That's where we used a regional model. This was executed by Hielke de Vries. He's also in the presentation watching along. And he used the regional model because the reason why we cannot use the other method is because the global climate models have a really low spatial resolution for example, of 100 kilometers. And to actually see a hurricane in your model, you need a lot higher resolution. Using such a regional climate model, Hielke looked at Hurricane Irma of 2017 that came by Sint Maarten, and he was able to simulate this hurricane well in his model. And in the future weather experiment, he looked at what this storm will look like in a warmer climate. So from these projects, we concluded that we don't see an increase in frequency of storms and hurricanes for Bonaire, so for the southern islands in a warmer climate, but that for the northern islands, so for Saba and Sint Eustatius, the frequency of the hurricanes of the strongest category will increase. And from the future weather experiment, we see that if Hurricane Irma took place in a warmer climate, that the max wind speed and the maximum precipitation of the hurricane would increase a lot. So that would mean that these the intensities of these storms and hurricanes increases in a warmer climate. So these were the results of our climate scenarios, and they are really important input for impact and risk assessments. That's also how they what are used in the PARATUS framework, for example, but also for the islands we look at. There's, for example, a climate impact atlas being made. Also, we use them in the multi-hazard dashboard or at the early warning center that we have at KNMI. And they are also, of course, very, very important for policy development. So for the Dutch Caribbean islands, there's now both adaptation and mitigation policies being made. And these climate scenarios serve really as a knowledge fundament for this. And of course, we do a lot of outreach to raise this public awareness. So how do these climate scenarios feed into PARATUS? Well, we look at the climate change, and we show how, for example, the climate change, for example, how the precipitation changes on average till 2100 now. And that's then goes into as information for into the impact analysis. And for us, it's really important then to know from these for these impacts, like what climate information is needed and how what we've done now, is this useful, or what exactly is needed. So, for example, we look at this mean change, but maybe there's more specific information needed on how drought periods change in a changing climate. So also within PARATUS, we make the scenarios adaptable to other regions or other islands within the Caribbean. So we have now developed these climate scenarios and our code and models for the 3 specific islands. We make sure that this is adaptable to different regions. So the scenarios came out at the beginning of October, and thereafter we visited Bonaire also to present our climate scenarios there, and but also what was even more important, to get input from stakeholders. And this is what you can see here. This was, for example, a stakeholder meeting to discuss with them what impacts they already experience on Bonaire or what impacts they expect to experience. And for example, 2 differences we already saw between the scenarios as we have developed them now and what the needs are from stakeholders is, for example, the difference in time horizon. So we make scenarios until 2100, but the communities or the decision makers are not planning that far ahead. They're planning for coming decades and then, for example, need more specific information for these coming decades. So there's more of an interest in the extremes of the data. As of course, people don't live in this average climate. Maria, do you have a question? Okay. So that was the presentation. So for me, the take-home messages are, from the most important messages from the scenarios is that it really gets warmer and drier in both seasons. That the sea level rise in 2100 reaches between 30 centimeters to 1.30 meters. And that for Bonaire, there's no increase in the frequency of storms and hurricanes, but for Stava and Statia, the strongest hurricanes become more frequent and the intensities of these storm and hurricanes get stronger. So this is what we've published in the BES climate scenarios, which is also available on our webpage in English, so you can read it up. So yes, this was the end of the presentation. So there were no questions yet so far, but I wonder if there's any questions or input now.
Thank you so much, Iris. So